Okay, students, let's start working on our problems for chapters 4, 5, and 6, okay? So we're on chapter 4. We're on page 130. Okay? All right, let's look at number 15. All right, and it says we have a compact car that has a maximum acceleration. I got a person in here driving it, and its acceleration max is 4 meters per second squared. Okay. Now, that is when it has only what? A driver and the car. And so the driver and the car has a total mass. So the mass of the driver and the car is 1,200 kilograms. Okay. What is its maximum acceleration after picking up 4 passengers and luggage, adding an additional 400 kilograms of mass? So we go down here and we pick up more people. And so we pick up what? An additional 400 kilograms. And so that gives us a mass total of 1,600 kilograms. So now we want to find the acceleration after they pick up those 4 people in their luggage. So we know Newton's second law, F is equal to ma. And so if we solve for A, it's the force over the mass. So let's find what the force was originally. Well, we had a 1,200 kilogram car, and its acceleration was 4 meters per second squared. Okay. And so that equals what? 4 times 12 is 48. So it's 4,800 divided by the total mass, and we're going to say total, which is 1,600 kilograms. And we get an acceleration of 3 meters per second squared. Okay? All right, now let's look at problem number 21. Okay, we're still on the same page, still on the same chapter, chapter 4, page 130. We got a figure 4.21 shows an object's acceleration versus time, acceleration versus force graph. What is the object's mass? So the graph looks something like this. And we have 1, 2, 3, 4, and that actually continues on up. And it's straight. Okay. So this is 4, and this is meters per second squared. 3, 2, 1, 0. And then we have time intervals. 3 and then 4. And I know that's not the scale, but pretend, okay? 0.5, and this is what? This is newtons. This is force in newtons, okay? All right, so we've got 0.5. Excuse me. Let me see if I can make that a little bit more symmetrical. All right, let's redo that. All right, so that's a little better, okay? All right, so we got what? We got 0.5, and then we got 1, okay? All right, so it tells us what is the object's mass. So we want to know the mass of the object, okay? Well, we know Newton's second law, F is equal to ma, and so m is equal to F over A, okay? All right, so basically what we need to do then is take the slope of the line, and let's just pick our points right here, and by the way, they're supposed to meet right there, and right here where the line, and I didn't draw it exactly through the corners, but it does go through the corners exactly. So basically what we're doing is the slope of the line, because look, force, let's see, did I do it backwards? F's equal to ma, so m is equal to F over A, right? Yes, F over A. So the force divided by the acceleration, okay? All right. So let's do the slope here. So let's take F1, which right here is 1 Newton. This will be 1 Newton minus, what is this going to be, 0.25 newtons? Yeah, 0.25 newtons. And then the acceleration here is what, 4 meters per second? Yeah, 4 meters per second squared minus 1 meter per second squared. So we have what, 0.75 newtons divided by 3 meters per second squared. Okay, and so what do we get? So we get 0.75 we get what? We get a mass of 0.25 kilograms, or 1, 2, 3 be 250 grams. Okay. All right, so that's how you do number 21. Real easy problem. And then let's look at number 25. We're on page, still on chapter 4, page 131. Okay. All right, and then it says we got a 55 kilogram skater. Okay, so you draw it. So you got a skater here. All right, and the mass of the skater is 55 kilograms. Okay, and is gliding along at 3.5 meters per second. Okay, so that's going to be what? The initial velocity, isn't it? 3.5 meters per second. All right. Then it says 5 seconds later. So after 5 seconds, the final velocity is what? 2.9 meters per second. Okay. What is the magnitude of the kinetic friction acting on her skates? Okay, so we want to know the magnitude of the kinetic friction. Well, we know that friction, that Newton's second law, F is equal to ma. Well, guess what? We can also substitute friction there. So the kinetic friction, which is going to be in the opposite direction, by the way. All right. Let me do this. I'm getting a little bit crammed in here. Okay. So let's do this. So kinetic friction is that way. Friction's always opposing. And since friction's a force, we can write it this way. Now we know it's in the opposite direction. We can write it this way, can't we? All right. F's equal to ma. But now hang on just a minute. We don't have acceleration. Well, that's okay. That's not a big deal. Okay. All right. Now it does ask for the magnitude of the kinetic friction, right? Okay. Well, so we know that F's equal to ma due to Newton's second law. It is in the opposite direction. Kinetic friction is. I forgot my K on there. All right. But now look, we have the initial and final velocity. And we have a time interval. So we remember from our kinematics that acceleration is equal to what? V final minus V initial over the change in time. All right. So let's substitute that in, and let's say the kinetic friction then is equal to what? Well, since we don't have acceleration, but we do have velocity, let's just substitute this right there. And so we have what? So we have the mass times what? V final minus V initial over the change in time. So now let's plug in. We got 55 kilograms. All right. Times, well, the final was what? 2.9 meters per second minus 3.5 meters per second divided by 5 seconds, right? And so when we do all that math, what do we get? All right, well, let's just see. So we got 2.9. We know that's going to be a negative value, 2.9 minus 3.5. All right, and then divided by, which is negative 0.6, and then divided by 5. And so we get negative 0.012. And then we multiply that times 55. And we get negative 6.6 newtons, don't we? Okay, because this is acceleration. Acceleration times mass is what? Force, all right? So we get negative 6.6 newtons, okay? Now notice it asks for the magnitude, and remember anytime you ask for the magnitude, it always has to be positive because that's the scalar quantity. So then it would be 6.6 newtons. That would be your final answer because it asks for magnitude, okay? All right, and does that make physical sense? Does that sound reasonable? Sure it does, okay? You're going to have some friction, okay? Even though you're on ice, you're still going to have a little bit of friction. Not a whole lot, but a little bit, okay? All right, so that was number 25, and let's look at one more, number 46. Okay, we're still on page 131. Okay, so let's look at number, what did I say, 46, yeah. Okay. All right, another simple problem. Most of these problems are not too hard, okay? All right, so 46 says we got a squid uses jet propulsion for rapid escapes. A squid pulls water into its body and then rapidly ejects the water backward to propel itself forward. All right, so we got a squid. Okay, so we got a squid. All right. Yeah, I know they're not round, but just pretend, okay? All right, and so the mass of the squid is 1.5 kilograms, okay? And it says, not including water mass, can accelerate 20 meters per can accelerate at 20 meters per second by ejecting 0.15 kilograms of water. All right. So it can accelerate this way at 20 meters per second squared by ejecting 0.15 kilograms, okay, kilograms of water, right? What is the magnitude of the thrust force on the squid? Okay, so what is the magnitude of the thrust force on the squid? All right, so we know Newton's second law, F is equal to ma, okay? So let's plug everything in. The mass of the squid is 1.5 kilograms, and its acceleration is 20 meters per second squared, right? Because what does it ask? It says, what is the magnitude of the thrust force on the squid? So the squid accelerates at 20 meters per second and has a mass of 1.5 kilograms. So it's accelerating this way, right? Okay, but now you've got to remember the force is in this direction too, but you've also got to remember Newton's third law. There's a force in that direction too. Okay, so this is the force of the squid, all right, and then that would be the what? That would be the force of the water, wouldn't it, going out of the squid. So that'd be the force of the water going out of the squid. All right, but we just want to know squid first, and so what do we get? What is the magnitude of the thrust force on the squid? Well, we get what? 1.5 times 20 is 30 newtons, don't we? So that's the magnitude of the thrust force. That's A. Now let's look at B. B says, what is the magnitude of the force on the water being ejected? All right. Well, okay. Now let me read that again. What is the magnitude of the force on the water being ejected? All right. So we use the second law, we use Newton's second law, or excuse me, what am I thinking? We use Newton's third law, and so guess what? It's also going to be 30 newtons, but it's in the what? It's in the opposite direction, isn't it? It sure is. Okay, and it asks for the magnitude, so we don't use a negative. It's in the opposite direction, but it wants to know the magnitude, so we just say 30 newtons. And you say, well, how can you say that? Because Newton's third law, folks, Newton's third law says that with every action there's an equal and opposite reaction, all right? So if there's 30 newtons in this direction, there has to be 30 newtons in the opposite direction. And then let's look at the last part, C, and then it says what? What acceleration is experienced by the water, okay? So we want to know the acceleration of the water, don't we? Okay, well, again, we go back to Newton's second law, F is equal to ma. We've already found out what the force was, so we want to know the acceleration. The acceleration is what? solve for acceleration, it's force over mass. The force was 30 newtons. The mass of the water is 0.15 kilograms. And so the acceleration of the water is what? Well, 30 divided by 0.15 is what? Is it 200? Yeah, that's 200 meters per second squared. Wow. That's really high, isn't it? And that makes physical sense, does it not? Now you see why. You say, well, now why is it so high? Because look, the force of the acceleration of the squid is this, okay, and that's its mass. So that's how much propulsion force there is. There has to be the same amount of force in the opposite direction. Well, since it's only ejecting a very small amount of water, then that means that water has to have a very high acceleration in order for it to match the 30 Newton force, okay? So the water coming out is extremely fast, okay? Has a very high acceleration, okay? All right, I hope these problems help, and I'm going to pause briefly and get ready for the next chapter. Okay, let's get started back now. Whoop. All right, so let's go open a new slide here. All right, so now we're on chapter 5, and we're on page 169. Okay, so let's look at number 6. It says an early submersible craft for deep sea exploration was raised and lowered by a cable from a ship. When the craft was stationary, the tension in the cable was 6,000 newtons. Okay. So we got water up here. We got a ship up here. Okay. Okay. Got a boom here. All right, and it's lowering a submersible craft. Okay, here we go. All right. And so it's lowering it down into the water. Okay. And it says that when it's stationary, the tension, so when the sum of the forces is equal to 0, it's not accelerating, then the tension is equal to 6,000 newtons, right? So the tension is in this direction, okay? We know the weight of the submersible is in this direction, right? Has to be. It has to be in the opposite direction because gravity's pulling straight down, okay? All right, so when it's stable, when the craft is stationary, it's 6,000 newtons. When the craft was lowered or raised at a steady rate, in other words, it's not accelerating. Steady rate, all right, steady rate equals 0 acceleration, okay? That means it's moving with a constant velocity, okay? So that means the tension in the cable does not change. Are you with me? All right, so it's being raised and lowered at a steady rate. The motion through the water added an 18 Newton drag force. Okay. All right, so if the submersible is going down, okay, then the drag force is going up, right? If the submersible, okay, if the submersible is going up, then the drag force has to be down. It has to be in the opposite direction, right? Think about a drag force being like friction, okay? Okay, so let's look at A, and so A says what? It says, what was the tension in the cable when the craft was being lowered to the seafloor? So let's look at this situation right here first. All right, so now let's write our equation. Well, we know that the sum of all forces is equal to what? Well, we've got the tension minus the gravity, or the weight, excuse me. All right, and since it's moving at a steady rate, that is the weight. Okay, you follow me? Because look, T minus mg is equal to 0. Then that means T is equal to mg. That's how I got that. You say, well, how do you know it's T minus mg is equal to 0? Tension is always up. The weight of the object is always down. Since it's moving at a steady rate, there's no acceleration, so the sum of all the forces is equal to 0. So that's how I come to that. So the tension is equal to the weight since it's not accelerating, okay? So the sum of all forces, now remember, all forces is all forces, tension, weight, friction, normal force, okay? All right? And then we have what? Well, which way is the drag? Well, look, if it's going down, the drag is up, so that's plus D. All right? Which is equal to 0. So now we want to find the tension. So then we write our equation, we solve for tension, we add mg to both sides, so it'd be mg minus D, and we subtract D for both sides. So let's plug in, then we've already determined that mg and T are the same. So we do what? So that's equal to 6,000 newtons minus 1,800, gummit, 1,800 newtons is equal to 4,800 newtons, right? This is an easy problem. I love these kind of problems. Oh, shoot, not 4842. My bad. Miscalculated there in my head. Long day. 4,200 newtons, okay? Now that's A. Well, now what about B? All right, now let's look at B. B says what? B says what was the tension in the cable when the craft was being raised from the sea floor? Okay, so raised from the sea floor. So what was it when it was being raised? So that's going to be this scenario right here. So this is lowering, okay, and this is raising. All right, well, let's do it then. So the sum of all forces is equal to the tension minus mg. All right, now look at D. D is in the opposite direction. Minus D is equal to 0. So then the tension is equal to what? Add mg to both sides and add D to both sides, mg plus D. So then the tension is what? 6,000 newtons plus 1,800 newtons. So the tension is equal to 7,800 newtons, okay? So that makes physical sense, does it not? Because it will have more tension coming up than it will be going down, okay? So that should make physical sense if you just think about it a little bit, okay? All right, let's look at another one. Let's look at number 24, okay? Oh, yeah, this is a good one, too. All right, 24. And we're on page 170, chapter 4. Oh, excuse me, chapter 5. All right, so mountain goats can easily scale slopes angled at 60 degrees from horizontal. What are the normal forces and the static friction force acting on the mountain goat that weighs 900 newtons and is standing on such a slope? Okay, so we got our mountain slope right here. Okay. All right, and so that's close to 60 degrees, and we got an silly old goat up here. All right, there's his horns. All right, there's the old goat. Okay, let me erase the 60 degrees, move it over a little bit. So 60 degrees is right there. Okay. All right. Now let's draw our vectors here. Okay. All right. Now notice he's on a slope. So we need to label all our forces. So we know that the weight or gravity is pulling down. That's mg. We know the normal force is perpendicular to the plane that the goat is on. And we know that a normal force, if you watched our videos, we know that the normal force, it's not accelerating up and down. The goat's just standing there. So it's not accelerating up and down. It's not accelerating this way. So we know that force normal minus mg is equal to what? 0. Now that's when it's on a flat surface. This is when it's on a flat surface. But what about when it's on a tilted surface? Okay. All right, well now notice that weight is not pulling this way, it's pulling this way. So let's finish our right triangle. And this is mg. Then what is this right here? This right here is mg sine theta. You say, where in the world did you get that? Look, right here, y'all, look. Okay, that is actually the direction the weight, that is the direction of the force that the weight has on the goat because it's at an angle. Yes, weight pulls straight down, but he's angled. So the weight force is being affected by the angle of the slope. And look, opposite over hypotenuse, this is mg. That right there is mg, okay, or gravity, or mg, the weight. Okay? So look, opposite over hypotenuse is sine. Now what is this right here? This here becomes mg cosine theta. Because look, the normal force on a flat surface is that right there. Well, when it's angled, then it becomes, look, adjacent over hypotenuse is cosine. So that becomes mg cosine theta. Okay? So now you say, well, what is the static friction force? Well, the static friction force is what? All right, well, we were not given a coefficient of static friction, but that's okay. That's okay because it's not moving. The goat is not moving, okay? So then the static friction is equal to what? Well, the static frictional force, since normally on a flat surface it's like this. See, look, you got a box, normal force, weight, okay? All right, but now it's angled, so it has to be this, doesn't it? Well, see, that matches this. See right here? That matches this, okay? But it's angled, so it's mg cosine theta, okay? So to find the static force, excuse me, not static force, that's the normal force or the y force, okay? So that becomes what? mg cosine, I got to correct that, theta. So that's the normal force. My bad. This is force normal. I think your book uses a lowercase n, and again, where do you get that? From this right here, okay? Because it's not accelerating. It's the sum of the forces is equal to 0. So the normal force is equal to mg cosine theta, and the frictional force. All right, now look, the goat's standing this way. Gravity's wanting to pull it this way. Well, which way is the frictional force? Well, it's this way. So static friction's this way. All right, now which vector matches that? Well, this one right here. This vector and that vector, those match up, don't they? Yeah, I could have drawn it right here. And you say, well, how do you know it's the same length? Because it's not moving. It's not moving. So then the static friction is equal to what? Well, it's equal to mg sine theta. Okay? Everybody with me? I sure hope so. Okay? All right, so let's just plug everything in. Now, the weight of the goat is what? 900 newtons. And you say, well, you didn't say that. You're saying all this mg stuff. Now, come on, look, y'all. Weight is equal to mg, all right? So the weight of the goat right there is 900 newtons. Mg is weight, all right? It's there, y'all. You just got to look. So we got to do what? Now, where was I? So we got to find what are the normal force and the static friction force. So we don't find the weight, we're finding the normal force. All right, but still weight's there, weight's here, okay? So let's find the normal force, Fn, and I like to write it that way, force normal. You can use the little n if you want to. And so the weight was what? 900 newtons times what? Cosine of what? 60 degrees. And what do we get for an answer? All right, well, let's see. We get, what do we get? We get 900, 900 times the cosine of 60. And we get what? We get 450 newtons. Okay, so we get 450 newtons. So that is the normal force. Now, look, there's not it's not accelerating. So there's actually there's no force necessarily in the y. Well, there is, there is, because of the normal force, okay? All right. Okay? Because this is in the opposite direction. Now, what about the static friction force? Well, that's going to be 900 newtons sine of 60 degrees. And what does that come out to be? Well, we got 900 times sine of 60. And we get what? We get 779.4. You could actually probably round it up to 780. So you get 779.4 newtons, or you could say 780 newtons, because there's 3 sig figs here, 3 sig figs there. Okay, the 60 degrees does not count because it's considered like a constant. Okay, all right. So as Colonel Stamper used to say, that's grocery store arithmetic, isn't it? Okay. All right, so that was number 24. Now let's look at number 28. We're still on page 170, so we got number 28, and that's page 170, okay? And so we got number 28, and we've got a 4,000 kilogram truck is parked on a 7-degree slope. Okay, so let me see if I can draw this. There's the horizontal. Let me make kind of a gentle slope. Okay, so we got a truck. And it is parked on a 7-degree slope, 7 degrees. And the mass of the truck is what? 4,000 kilograms. So the mass of the truck is 4,000 kilograms. Notice how I write everything down, label everything, write it down. 7-degree slope. All right, now, all right, let's draw our vectors. We know we got a force normal. We know we got a vector this way. What else do we have? Well, we also have frictional force this way, static friction, because it's parked on a slope. We know that the weight of the truck goes in this direction, and what vector matches this vector? Right here. Okay? Those two match because it's not moving. All right? So this we know is mg cosine theta, and we know this is mg, and this right here is mg sine theta. Again, how do you know, Ms. Shields? Look, right here. See that vector right there? That is opposite over hypotenuse is sine. This right here, see the angle? There's the angle, 7 degrees. You say, how do you know it's 7 degrees? Oh, come on now, don't forget your geometry. If this angle is 7 degrees and you draw these vectors, that angle has to be 7 degrees because it forms a right triangle, okay? So adjacent over hypotenuse is cosine, all right? Okay, now, okay, and it does say it's parked, right? Yep, how big is the friction force on the truck? So we want to know this right here, don't we? So we're looking for static friction force, question mark, okay? Well, which vector, which one matches up? Well, this one right here, doesn't it? Okay? Because we know what? Well, first of all, you got to determine this, that the sum of all forces is equal to 0. How do you know that? Because it's not accelerating. It's sitting still. It's not accelerating. Acceleration is 0, so therefore the sum of the forces is 0. Doesn't mean there's not forces there. I said the sum of the forces, okay? So what do you have then? You have the frictional force. So if you do this right here, you got the sum of all forces. You got the frictional force, which is this way, because the weight is this way, isn't it? The weight is pulling it back that way is equal to 0. So how do we determine weight? Now we don't just go here. Remember, it's at an angle. So then the static friction force is equal to the weight. Well, how do we find weight? Look right here. This vector and this vector, that's actually your weight vector. mg sine theta. This is actually your weight vector. You say, how do you know that? Well, I thought weight was straight. It is, but it's tilted. You can't forget that. And so therefore the weight is being affected by the what? By the angle of the slope. Okay? If it was, all right, look, if it's on a flat slope, the sine of 90 is 1. Okay, but it's not on a flat slope. So therefore the sine of 7 degrees is going to affect the weight of the truck, isn't it? It sure is. Okay, so then it's equal to what? It is equal to mg sine of theta, isn't it? Is that correct? Yes, it is. All right. Now, we've also forgot one other thing. We forgot about gravity. Now, you should remember what gravity is, 9.8 meters per second squared. And you say, well, wait a minute, isn't it negative? Is it not negative? Okay. Well, we're wanting to know, does it say the magnitude? Let me go back and read it. How big is the friction force on the truck? Well, it doesn't say magnitude, but we're to assume. You say, well, that gets us in trouble. Well, in actuality, it doesn't, because look, all right, here's the negative right here. See, I'm not trying to fudge on the math here, not trying to fudge on the rules, but there's a reason for all the madness. Now look, let me explain why. When you write your equation, the frictional force is in the upwards direction, that's positive. The weight is in the negative direction. Right there it is. So there's your negative 9.8 right here. You don't say negative times negative. It's already negative. It's equal to 0. So when you solve for the frictional force, it becomes positive. Because remember, you say, how do you know that? The frictional force is going up the incline. If you draw your Cartesian coordinates right here, here's x, here's y. Notice that's in the positive x direction. So yeah, we're doing everything right. Okay, so frictional force is equal to what? 4,000 kilograms, right? Okay, times 9.8 meters per second squared times sine of 7 degrees. And what do we get? I think we're going to get something close to 4,800. I think that's right. So we got 4,000 times 9.8 times the sine of 7 degrees. And we get 77.3 newtons. So we could actually say 4,800. You say, well, now how do you know to do that? All right, look how many sig figs are there. Look how many sig figs is right there. Okay, you got to watch those sig figs. You say, well, what about that 7 degrees? You ignore that because it's considered to be constant because it's sine and cosine, okay? All right, so it'd be 4,000 degrees, so it'd be what? 4,800 newtons if you follow the sig fig rules, okay? All right, 4 sig figs, okay? All right, okay. All right, I hope that makes sense. All right, now we've got one more to do. Let's look at number 42. Okay. All right, so number 42, still on chapter 5, and number 42 is on page 171, okay? All right, so we got a 2,200 kilogram truck that puts its front bumper against the rear bumper of a 2,400 kilogram SUV. All right, so let's draw it. So we got a truck here. All right, and there's the bumper. And then it puts its bumper on a what? So this is the truck, and that's the SUV. And so the mass of the truck, is what? 2,200 kilograms. And the mass of the SUV is what? 2,400 kilograms, okay? All right, and then it says puts the bumper to bumper, puts its front bumper against the rear bumper, okay? And to give it a push, with the engine at full power and good tires on good pavement, the maximum forward force of the truck is 18,000 newtons. All right, now look, we know if their bumpers are touching, then the force of the truck is also going to be equal to the force that's applied to the SUV, right? Force of the truck is applied to the force of the SUV, so they have to be equal. So that force is what, 18,000 newtons? I think that's what it said. Yeah. What is the maximum possible acceleration the truck can give the SUV? All right, well, this is a Newton's second law problem, so we know Newton's second law says F is equal to ma, so that means then that what? Acceleration is equal to the force divided by the mass. But now notice we've got two masses here. So in other words, what would be the maximum acceleration if the maximum force that it's pushing on the SUV with is 18,000 newtons? So we got 18,000 newtons. All right, now look, we've got two masses here. We got the mass of the truck, 2,200 kilograms, plus the mass of the SUV, 2,400 kilograms. So then the acceleration would have to be what? Well, we've actually got 4,600 kilograms total. So 18,000 divided by 4,600 is equal to what? 3.91. Yeah, we get 3.91 meters per second squared, okay? And how would we write that answer? Well, let's see. We actually got two significant figures because there's no decimal. So you could say 3.91, that would be good enough, meters per second squared. So that is, what are we on? Part A, so that's A. And what's part B? All right, part B says, at this acceleration, what is the force of the SUV's bumper on the truck's bumper? Okay. You say, well, Mr. Shields, I don't know. All right, now look, this is a Newton's third law problem. This is a statics problem, okay? All right, so the net force of the SUV, so we know the S, we know the net force, so that has to be M times A, doesn't it? It sure does. All right, well, we know what the acceleration, now you say, well, wait a minute now. This previous question says, what is the maximum possible acceleration of the truck on the SUV? All right, now look. They're both touching. They're both moving together, okay? So this means what? This means that the truck and the SUV both have an acceleration of 3.91 meters per second squared. So if I want to find what the acceleration is of the SUV,
on the, what is the maximum possible, no, wait a minute, at this acceleration, what is the force of the SUV's bumper on the truck's bumper? So if I want to know what the force is here onto there, well, it's still a Newton's second law problem. It's Newton's third law and second law. It's third law when we look at how both are accelerating at the same rate, okay, at the same acceleration. But now look, what was the mass of the SUV? It's 2,400 kilograms, okay? And what was the acceleration? 3.91 meters per second squared. So what do we get for an answer? So we get 2,400 times 3.91, and we get 9,384. So we get 9,384 newtons. All right, well, does that make physical sense? Well, sure it does, because the total force was 18,000 newtons. So if the force of the SUV on the truck is 9,384, you could go ahead and round it to 9,400 if you wanted to. Then what would the force of the truck be? Okay. Well, then the force of the truck would be 18,000 minus, so look, so it'll be 18,000 minus 9384, and we get 8616, okay? So the force of the truck on the SUV would be what? 8616, okay? All right. Okay, because when you add them both up, what do you get? You get 18,000, all right? All right. So I think that's all of this chapter. Yep, that's all of this chapter. I'm going to break, pause for a second, and get ready for the next chapter. Okay, students, let's look at chapter 6 now. So now we're on chapter 6, and we are on page, crazy head me. All right, we are on page 200. Okay, so let's look at number 6 on page 200. The horse on the carousel is 4 meters from the central axis. All right, so we're going to draw this looking down. All right, and so here's the horsey, right there, okay. And the horse is 4 meters, all right, so the radius then is, 4 meters from the central axis. That's how far the horse is, okay. All right. Okay. If the carousel rotates at 0.1 revolutions per second, how long does it take the horse to go around twice? Okay, so then it rotates. Its rate is what? Its rotation is what? 0.1 revolutions per second, right? So how long does it take for it to go around twice? Okay. How long does it take for it to go around twice? Okay. Well, basically what we're trying to do is we're trying to find the time, aren't we? But now we got to remember that we can't look at this in revolutions per second. Okay. That's actually 0.10. Yeah, put a 0 in there. All right. That looks horrible. All right, erase. Let me start over. So it rotates at 0. Dad blast it. Slow down. 10 revolutions per second. There we go. So we want to find what? We want to find the angular speed, don't we? Yeah, we got to find that first. And angular speed is in radians per second. Well, how do we do that? Well, we know that the angular speed is equal to the revolutions, 0.10 revolutions per second, times what? Times, well, how many radians are in one revolution? Now, if you remember your trig and your geometry, it's 2 pi radians per 1 revolution. You say, how did you know that? One complete circle is 2 pi radians, all right? So your revolutions cancel out. And what do we get? Well, we get 0.1 times 2 times pi, and it's 0.628. So it's 0.628, and that's radians per second. All right, so now we know the angular speed. Now listen to me right now. You do not put your calculator in radian mode. The only time you put your calculator in radian mode is when you're doing trig functions with radians instead of degrees. So in other words, if you want to take the cosine of pi over 2, then you have to put your calculator in radian mode. So we don't need it in radian mode. You leave it in standard computational scientific calculation mode. You don't have to put it in radian mode, all right? All right, so 0.628, and you, by the way, you use the pi button on your calculator, all right? You use the pi button. You don't type in 3.14, you use the pi button, okay? Okay, so now we know that's the angular speed, right? Okay, so now we can find the actual time it takes to go around twice. Well, we know from our lecture and from looking through our notes and everything, is this a two-part question? Yes, it is. So A, then, we know that angular speed is what? Is the arc, the arc distance divided by what? The change in time, right? Okay. Okay. So let's look at this then. Now, we can leave this in revolutions, this part, but we're going to need what I calculated right here for the second part. That's why I went ahead and did it. All right, because look, it's 2 revolutions, right? And we know that the time interval, we got to find for the time, solve for the time interval. So time is equal to the amount of revolutions, or the arc, divided by the frequency, okay? And since we're going to leave it in revolutions per second because it's 2 revolutions over 0.1 revolutions per second, the revolutions cancel out, and we are left with what? 20 seconds. So that's how long it takes. All right, now let's look at part B. Part B says what? How fast is a child on the horse going in meters per second? Okay, well, if you go back and you watch our videos, you'll see that the velocity, and this is the linear velocity, okay, this is not this is the velocity in a straight line path. The velocity is equal to what? Omega times r. All right, now remember we've already found omega right here. So we say 0.628 radians per second times, all right, the radius was 4 meters, and so what do we get? So we get what? We get 0.628 times 4. We get 2.51 meters per second. So we get 2.51 meters per second. You say, now hang on just a minute there, Chief. Where does my radians go? Well, radians is one of those units, I hate to say it's unitless, but in a way it is, okay? Because we don't measure in radians, we measure in degrees, and we measure in what? Meters, okay? All right. Now we can measure an angle in radians, but again, and see, degrees is kind of the same way, all right? So basically what we're saying here is that it in a way it cancels itself out, or it cancels out. And you say, how did you get that? If you'll go back and look at the definition for the arc length, how to measure arc length, you'll see that it cancels out, okay? All right. So 2.51 meters per second, okay? All right, let's look at another one. Let's look at number 17. Yeah, number 17. We got a typical running track is an oval with 74 meter diameter. Okay, 74 meter diameter. Wait a minute. Now I'm reading the wrong problem. I'm sorry. I was reading number 12. All right, we got a 1,500 kilogram car drives around a flat 200 meter diameter circular track. Okay. So you got a circular track, okay, so you got a circular track, and, all right, okay, and we'll draw the radius like this. Oh, dang it. And here's the car, okay. All right, and so we'll measure the radius from here to here. That's the radius, all right. And it says what? It says that the mass of the car is 1,500 kilograms, okay. and the drives around a 200-meter diameter circular track. So if the track is 200 meters, so if the diameter is 200 meters, then the radius is 100 meters, and that's what we need right there, okay? Okay, what are the magnitude and direction of the net force on the car, and what causes this force, okay? Oh, and by the way, we didn't write down how fast the car was going. The velocity of the car is 25 meters per second, okay? All right, so we've got to find what? The magnitude direction of the net force. So we got to find force, net, direction, okay? That's a vector symbol. Gummit. There we go. We got to find force, net, and its direction. But we got to find magnitude and direction, okay? Magnitude and direction. All right, so let's look at this. This is actually a what? This is actually a centripetal acceleration problem, okay? Because the car is going around the track, and if any of you have ever noticed when you're in a car, on a bicycle, motorcycle, and you hit a curve, you notice that you accelerate. You also notice that your body wants to keep going straight. That's why you get slung to one side of the car or the other, okay? You usually go in the opposite direction the curve's going. That's why you have to lean into the curve. So we know that the centripetal acceleration then is equal to the velocity squared divided by the radius, okay? All right, so let's plug everything in. We got 25 meters per second squared over 100 meters, and what do we get for an answer? We get an answer of, let's see, we got 25 squared divided by, which is 625, divided by 100, and we get 6.25 meters per second squared, okay? 6.25 meters per second squared. Now, how do we know which way the acceleration is? Okay, well, now if you remember anything about centripetal acceleration, that means it is what? Center seeking. So the centripetal force has to match the centripetal acceleration, so it is towards the center of the circle. So it's towards the center of the circle, okay? Has to be, okay? Because, look, because of centripetal acceleration. All right, so now we want to know the force. So how much force would that be? Well, Newton's second law says F is equal to ma, and the car was 1,500 kilograms times acceleration, 6.25 meters per second squared. And what do we get? Well, we get 1,500 times 1,500, and we get 9,375 newtons. Okay? 9,375 newtons. Now, we could also substitute, we could have also done it this way. We could have done the centripetal acceleration this way, mv squared over r. Okay, because look, acceleration right there, we'll substitute right here. We could have also calculated it that way. All right. All right, so that's number 17. Now let's look at another one. Let's look at number 34. Yeah. All right, so number 34, and we're on page 202. By the way, what page was that on? Number 17 was on page 201. My bad, that's on 201. Okay. All right, so the centers of a 10-kilogram lead ball and a 100-gram lead ball are separated by 10 centimeters. So you got a lead ball here, and you got a lead ball here, and they are separated by 10 centimeters. And the mass of this one is 10 kilograms, and the mass of this one is what? 100 grams. Now, you probably noticed something right out the gate. And they're separated by 10 centimeters. So let's convert this to kilograms. That's 0.1 kilograms. And let's convert that to meters. That is 0.1 meters. Okay, we have to do that, all right? Because remember, when we're looking at forces, it has to be in kilograms and in meters. Okay. All right, so what gravitational force does each exert on the other? So what gravitational force is exerted one on the other, okay? All right. Well, how do we determine that? Well, we know that Newton's first law says the F of 1 on 2 is equal to the what? The force of F2 on 1, okay? And it's actually in the opposite direction. Okay, but we're going to keep it simple here. All right. So then Newton's law of gravitation says that we've got force is equal to G, that's Newton's gravitational constant, times the mass of 1 times the mass of 2 divided by the radius between the two objects squared. So Newton's law of gravitation is what? Well, that constant is 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared, right? Yeah, kilogram squared, all right? Times the mass of 1, which was 10 kilograms, times the mass of 2, which is 0.1 kilograms, divided by the radius. And the radius, all right, now look, the distance, now let's make sure we read this right. Yeah, they are separated by 10 centimeters, so that's the radius, and that would be radius squared. Okay, so that's going to be 0.1 meters squared. And so now let's do all this ungodly arithmetic, and this is A, isn't it? Yeah, I believe it is. Yeah, A. Okay, so let's do all this. So we got what? So we got 6.67 to the exponent of negative 11 times 10 times 0.1, and then divide that by 0.1 squared. And we get 6.67 to the negative times 10 to the negative 9th newtons. So we get 6.67 times 10 to the negative 9th newtons, okay? Now we could go ahead and round that up because, look, you got two significant figures. Did I write that down right? Yeah. So you could just say 6.7 times 10 to the negative 9th, okay? Oops. Oh, for crying out loud. Why can't I write right? Okay. All right, that's A, isn't it? All right, now let's look at B. What is the ratio of this gravitational force to the weight of the 100-gram ball? Okay. All right, so we got 6.67, so the force is what? And that's Newton's law of gravitation was 6.67 times 10 to the negative 9th newtons. All right, so we want to know what the weight, what is the ratio of that weight to the ball, okay? All right, well look. The weight of the ball is mg, and the mass was 0.1 kilograms, okay? Goodness gracious. 0.1 kilograms, okay? All right. And we know g is 9.8 meters per second squared. We're not going to worry about the negative because we're just wanting to know the weight. We're just taking the magnitude. And so then we have what? So the weight is equal to what? Why did I do that? So we got 0.1 times 9.8. 0.1 times 9.8 is what? 0.98. 0.98 newtons, isn't it? Sure it is. All right, so now let's do the ratios. All right, so we're going to take the 6.67 times 10 to the negative 9th newtons and divide it by 0.98 newtons, and what do we get? So 6.67, or if you want to use 6.7, you can. So we'll say 6.67 to the negative 9th divided by 0.98, and so what do we get? We get 6.0, we get 6.80, let's just say 6.81 times 10 to the negative 9th is the ratio, okay? So it's 6.81 times 10 to the negative 9th times what? It's comparing that, yeah, so that's the ratio or the amount of the what? The ratio of this gravitational force to the weight of the ball. Wow. It's not a whole lot, is it? Okay, all right. Okay, now let's look at our last problem, number 43, and this is still on page 202. So 43, and this is page 202, okay. All right, what is the free fall acceleration at the surface of Mars and at Jupiter? So what is the free fall acceleration at the surface of Mars and at the surface of Jupiter, okay? All right, well, now we know we've got to know a couple of things here, don't we? We've got to know the radius. We've got to know the radius of Mars, and we've got to know the radius of Jupiter. And so you have to go to the back of your book. I can't remember what page that's on. In the back. Oh, Lord. Yeah, it's on the very back inside cover of your book, back in the appendices. And so you have to look those up. They give you the mean radii. And we're looking at what? Mars and Jupiter? Yeah. Mars is 3.37. Yeah, and you've also got to get the mass. And it also gives you the mass on that page also. Okay, and the mass of Mars is 6.42 to the 23rd. Yeah. All right, so how do we find that? Well, according to Newton, that the gravitational constant of a planet on its surface is equal to Newton's law of gravitation times the planet's mass divided by the radius of the planet squared. Okay? All right, so let's do this calculation then. So G of Mars is equal to 6.67 times 10 to the negative 11th, and that is newtons meters squared per kilograms squared times what? The mass of the planet, again, I told you, look it up in the back of the book. The mass of Mars is 6.42 times 10 to the 23rd kilograms divided by the radius. You look that up in the appendices, and that was 3.37 to the 6th times 10 to the 6th meters, and that's squared. And so we get the gravitational constant of Mars is what? All right, let's do the math. Okay, so we get 6.67 to the negative 11th times 6.42 to the 23rd divided by 3.37 to the 6th squared. And we get 3.77. So we get 3.77 meters per second squared. So that's for Mars. And then you do the same thing for Jupiter. So that was, that was A, and this is B. And so we got for Jupiter, so we got 6.67 times 10 to the negative 11th newtons meters squared per kilograms squared times, then you look it up in the back of the book, 1.9 times 10, that's 90, times 10 to the 27th kilograms, divided by 6.99 to the 7th, 6.99 times 10 to the 7th meters, and that's squared. And so the gravitational constant of Jupiter is equal to what? So we got 6.67 to the negative 11th times 1.9 to the 27th, and then divide that by 6.99 to the 7th squared. And what do we get? We get 25.94. So we get 25.94 meters per second squared. Are you kidding me? Are you kidding me? That would kill you. That would crush you, more than likely. Well, let's see, though. No, wait a minute. 25.9, no, it wouldn't necessarily crush you. It's twice, almost 3 times the gravitational pull of the Earth, so you would definitely know it if you were on Jupiter, okay? It wouldn't crush you. Its atmospheric pressure would probably crush you, though, okay? All right, so that's it, y'all. I hope this helps.